So good day to everyone. Let me just introduce myself first. I am Engineer Adams Royce A. Janisha, a licensed civil engineer, a faculty member, a BSCE graduate, and a graduate student in the University of the Philippines, Diliman campus, with a specialization in structural engineering. And this is my email, adamsroycejanisha@gmail.com. So you can contact me here via email, or you can just search my name on Facebook or Messenger if you have any concerns. And welcome to my online lecture class. So our subject is CS003 Bridge Engineering. So this is a professional course that is being taken up by those students who have chosen structural engineering specialization. So before I start the discussion, I just want to have a little disclaimer here. This presentation may contain errors that will be corrected in class. It is the responsibility of the student to take note of these corrections. This may be considered as a supplementary material only and should not be used as a substitute to the class discussions and reading materials. Not everything that the student needs to know is included in these notes. No part of this presentation, photos, problems, etc., is owned by the instructor. Credit goes to the respective owners. Fair use of copyrighted materials was observed. And then I just want to have a little reminder to everyone that this PowerPoint presentation is a property of the instructor. No part of this presentation may be copied, photographed, printed, reproduced, shared, transmitted, translated, or reduced to any electronic medium or machine-readable form, in whole or in part, without prior consent of the instructor. So please refrain from sharing this presentation, especially on any online platform for distribution. So please refrain from doing so. So the references that I have used in my lecture on this presentation, first is the Bridge Engineering by Tonyas and Zhao. So this is the Bridge Engineering book, Design, Rehabilitation, and Maintenance of Modern Highway Bridges. So the latest edition is the 4th edition. And I recommend the students to grab a copy of this book because I will be using this as our main reference on this particular subject. Although this edition is still not readily available on the internet, so you can just grab a copy of this on the website of the publisher, which is the McGraw-Hill Education. So if your school has a subscription on the publisher, the McGraw-Hill Education, so I recommend to check on that, especially if you have a remote library. So please check this book because I will be using this as our main reference. Another reference book that I have used is The Design of Highway Bridges by Barker and Puckett. So this is the book. Although this book here, The Design of Highway Bridges, an LRFD approach, the 3rd edition, is still using the previous edition of AASHTO LRFD, which is the AASHTO 2010, and the 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 edition of AASHTO that we will be using on this subject is the AASHTO 2012 because it is the reference of our local code, which is the DGCS made by Department of Public Works and Highways. So this is the AASHTO 2012 that we will be using. AASHTO LRFD Bridge Design Specifications 2012 version, edition. So we will be using this. I recommend again to have a copy of this code. And lastly, our local code that I will be using is the DGCS, the Design Guidelines, Criteria, and Standards, Volume 5, Bridge Design, 2015, uh, from the Department of Public Works and Highways, Bureau of Design. So I have used ASHTO 2012 because as I checked our local code, it is still using the ASHTO 2012 edition of the code. Although there is already a newer version of ASHTO, but still, since our local code is still using the ASHTO 2012, so we will just stick to that edition of the code. And then lastly, last reference that I have used is Google for some images and video clips. So our intended learning outcome for discussion are this. At the end of the discussion, the students will be able to, number one, explain the definition of bridge engineering. Number two, explain the importance of the study of bridge engineering. Number three, state the origins of the modern highway bridge. Number four, define the different terms used in bridge engineering, especially the different parts of a bridge. And number five, define the different structure types used in bridge construction. So these are our goal for this discussion. So at the end of discussion, I expect the students will now be able to explain the definition of bridge engineering, explain the importance of the study of bridge engineering, state the origins of the modern highway bridge, define the different terms used in bridge engineering, especially the different parts of a bridge, and lastly, define the different structure types used in bridge construction. So without further ado, let us now address our first goal for this discussion, which is for you to be able to explain the definition of bridge engineering, and immediately after that, let us address our second goal, which is for you to be able to explain the importance of the study of bridge engineering. So before we start to define the subject bridge engineering, maybe we need to know first what is a bridge? Because as the subject tells us, bridge engineering, we can easily tell that the subject is all about bridges. So before we define bridge engineering, maybe we need to know first what is a bridge. So by definition, a bridge is a crossing structure erected or built over a communication route such as roads, railways, canals, or a natural obstacle such as watercourse, valley, etc., and allowing people, vehicles, animals, etc., to go easily from a point to another. So by this definition, we can see that a bridge is a structure. Structure erected over an obstacle, whether it is man-made, such as road, railway, canals, or a natural obstacle, such as watercourses, valley, etc., with the purpose of allowing people, vehicles, animals, etc., to go easily from one point to the other. Like, for example, if you have a very large highway that is being traveled by many speeding vehicles, and we want to cross the highway from one side to the other, we can just build a bridge over that obstacle, which is the highway, like a footbridge, for us to easily traverse the highway, the obstacle, from one side to the other without being hindered by the flowing traffic. Or another example, if we have a natural obstacle such as a body of water like this that you are seeing here on the picture or GIF, actually this bridge that you are seeing here is actually San Monico Bridge that connects Samar and Leyte. So you can see here there is a natural obstacle, which is the body of water that we have here, that prevents people from easily going from one point, from one side of the region to the other side. So instead of traversing the body of water using a boat or a plane, we can just build a bridge there for the people, for the vehicle, for the animals to easily go from one side of the region to the other side of the region. So in other words, bridges or bridge is a structure that makes our lives easier. It makes our travel easier. Instead of traveling a longer distance, it makes us travel a short distance by connecting a point to another. It enables us to pass through an obstacle, whether it is a man-made obstacle such as road obstacle, railway obstacle, canal obstacle, or a natural obstacle such as watercourses or bodies of water like rivers, and allows us to easily traverse or pass through those obstacles. It allows us to easily go from one point to the other. So with that, after knowing what is a bridge, let us now start to define the word or the subject bridge engineering. So what is bridge engineering? So by definition, bridge engineering is an engineering discipline branching from civil engineering that involves the planning, design, construction, operation, maintenance, and rehabilitation of bridges to ensure safe and effective transportation of vehicles, people, and goods. So we can see here the definition of bridge engineering. And we have known that bridge engineering is mainly focused on planning, design, construction, operation, maintenance, and rehabilitation of bridges. Actually, that is what differentiates bridge engineering from the other course or the other subject, which is bridge design. So, because if you don't know, bridge design is another course usually taken after the course bridge engineering. Although on our school, on our subject, we will no longer take bridge design, so we will tackle everything on the subject bridge engineering. So you can see bridge engineering is actually a broader course uh, than bridge design, because bridge design is mainly focused on one subject only, which is the design, while bridge engineering encompasses everything about bridges: planning, design, construction, operation, maintenance, and rehabilitation. Not only design, but also planning, design, construction, operation, maintenance, and rehabilitation. Unlike bridge design, it just mainly focus on the design of bridges. So you can see that bridge engineering is actually a very broad course, very broad subject that encompasses everything about bridges. So uh, you can expect on this subject that we have here, we will not be focusing on how to design bridges. Although we will tackle how to design bridges later on, maybe on the following weeks, but we will be we will not be focusing more on the design of bridges, but we will be focusing about everything about bridges, about engineering a bridge: planning, design, construction, operation, maintenance, and rehabilitation. So that is the definition of bridge engineering. So some of you might ask, why do we need to study bridge engineering? Or in other words, why do we need to engineer a bridge? Why is it important to study bridge engineering? Why is it important to engineer a bridge. So I will enumerate here some of the reasons why do we need to engineer a bridge. I will enumerate here how important it is to engineer a bridge. So we need to engineer a bridge because if the width of a bridge is insufficient to carry the number of lanes required to handle the traffic volume, the bridge will be a constriction to the traffic flow. Actually, this scenario is similar to having a large number of people inside a room with only one narrow exit door. Can you imagine what will happen if that large number of people will simultaneously exit the room with just using that single narrow door? So you can imagine they cannot simultaneously exit the room because the door that they are using, the exit door that they are using, is insufficient to cater the large number of people exiting the room. There will always be a congestion on that particular exit door that will eventually result to slow movement of the people. So that scenario is actually similar to what will happen if we did not engineer a bridge properly, if we did not plan it and design it properly. The tendency will be that particular bridge might have an insufficient width that is not adequate to carry the required number of lanes that is needed to handle the traffic volume. And the result will be there will be a traffic congestion because the vehicles or the traffic using that particular bridge cannot enter the bridge simultaneously. They have to wait one at a time because the number of lanes on that particular bridge is insufficient or are insufficient to cater the volume of traffic using that particular bridge. So they have to wait one at a time, and that will eventually result to very slow movement of traffic. That in other words, the bridge will that bridge that is not engineered properly can be a cause of traffic flow constriction. It will prevent the smooth flow of traffic. It will just result to traffic congestion if we did not engineer a bridge properly, if we did not design it to have a sufficient width that can cater the traffic volume on a particular location. So that is one of the reasons why do we need to engineer a bridge. So another reason why we need to engineer a bridge is because if the strength of a bridge is deficient and unable to carry heavy trucks, load limits will be posted and truck traffic will be rerouted. The bridge controls both the volume and weight of the traffic carried. So this is again another reason why we need to engineer a bridge. We need to engineer a bridge because it needs to have adequate strength to be able to carry heavy traffic such as heavy trucks. Because if we won't be engineering a bridge properly, if we will not be planning and designing it properly, the result will be there will be a limitation on its usage. There will be a restriction on its usage. There will just be a certain load limit that can be carried by the bridge. And as a result of that limitation, those traffic, like heavy trucks, that will not be satisfying the load limits will be needed to be rerouted. They must be rerouted to some other place if they will not be satisfying the load limits of a particular bridge. So again, that can be a result if we will not be engineering a bridge properly. There will be a limitation on its usage. It cannot cater all of the intended traffic that are supposed to be carried by it. There will be a limitation on its limit. There will be a load limit. There will be some traffic like heavy trucks that cannot be accommodated by that same bridge, and as a result of that, those trucks, those traffic that cannot be accommodated because of the insufficient design of a bridge that is not engineered properly. As a result of that, those those which are not satisfying the limitations of the usage of the bridge will be needed to be rerouted. So therefore, it is important to engineer a bridge properly so that there can be no restriction on its usage, so that it can cater all of the traffic that are intended to be catered by it. Another reason why we need to engineer a bridge is simply because bridges are expensive. The typical cost per mile of a bridge is many times that of the approach roadways. This is a major investment and must be carefully planned for best use of the limited funds available for a transportation system. So this is again another reason why do we need to engineer a bridge? Simply because bridges are expensive, meaning it's a very big investment, and we cannot just waste money on a structure that will just be used for a short period of time. Therefore, since bridges are an investment, therefore we have to properly plan it. We have to properly plan it. We have to properly design it. We have to properly construct it and operate it and maintain it and rehabilitate it if needed, so that our money that that will be used to build the bridge will not go into waste. So that is again another reason why do we need to engineer a bridge. Another reason why we need to engineer a bridge is this. When a bridge is removed from service and not replaced, the transportation system may be restricted in its function. Traffic may be detoured over routes not designed to handle the increase in volume. Users of the system experience increased travel times and fuel expenses. Normalcy does not return until the bridge is repaired or replaced. So again, this is another reason why do we need to engineer a bridge. Because if we will not be engineering a bridge properly, it may have a very short uh, useful life. Therefore, after some time, we need to stop the bridge from service, and if it will not be replaced immediately, the the transportation system of that particular region will not function as how it functions before when the bridge is there. Meaning there will be no longer normal life on that particular region because of the absence of the bridge. Say for example, uh, the vehicles that normally traverse a particular region from one point to the other using that bridge will no longer be traversing that same distances because the bridge is no longer there. It was stopped in service. Therefore, the vehicles must find another route to travel. And these other routes might cause the the travelers to have a longer route to traverse. Because of the absence of the bridge, rerouting another route must be sought by the users of the bridge, and sometimes it might cost them to travel a longer distance. Therefore, there will be an increase in travel time as well as fuel expenses, more fuel expenses because the distance that were normally traversed by the vehicles using that particular bridge will no longer be that the same distance as they used to before. So the last reason why we need to engineer a bridge is because a bridge is a key element in a transportation system. Since it likely controls the capacity, it has the highest cost per mile, and its failure will cause system fail. Balance must be achieved between handling future traffic volume and loads and the cost of a heavier and wider bridge structure. Strength is always a foremost consideration, but so should measures to prevent deterioration. The designer of new bridges has control over these parameters and must make wise decisions so that capacity and costs are in balance and safety is not compromised. So this is actually the reason why we need to engineer not only a bridge but every structure that we build. It's because we cannot build oversized structures like oversized bridges just to ensure that it will have adequate capacity or strength to accommodate the traffic volume that is intended to be catered by this particular bridge. Uh, we cannot build oversized structures just to ensure safety. We cannot build oversized structure to ensure that there will be adequate capacity to cater the intended traffic volume. Because we know that an increase in capacity incurs an increase, a corresponding increase in cost. So therefore, we cannot just build oversized structures just to ensure the safety of the users of our structure. We must balance this capacity to the cost of having this magnitude of capacity. Or in other words, our design must always be economical. So again, that is a reason, that is another reason why we need to engineer a bridge. Simply because our design must be economical. Our design cannot have over capacity because it will incur additional costs. We want our bridge to have a minimum cost that will still be balanced by an adequate capacity that will still ensure the safety of its users. And we can just achieve this if we will engineer a bridge. So therefore, we can see here that we need to engineer a bridge to ensure that capacity and costs are in balance, but still safety is not compromised. So we are now done addressing our first goal for this discussion, which is for you to be able to explain the definition of bridge engineering, as well as for you to be able to explain the importance of the study of bridge engineering. So we are now done addressing those two goals for this discussion. So we will now move on to our third goal for this discussion, which is for you to be able to state the origins of the modern highway bridge. So before we start on studying the bridge engineering that we have today, before we start to study the modern highway bridges that we have today, it is worthy to look back, to have a quick look back on the brief history of bridge engineering, especially how the modern highway bridges that we have today came to its conception as what it is today. Usually, a discourse on the history of bridges begins with a log across a small stream or vine suspended above a deep chasm. This preamble is followed by the development of the stone arch by the Roman engineers of the 2nd and 1st centuries BC, and the building of beautiful bridges across Europe during the Renaissance period of the 14th through 17th centuries. Next is the Industrial Revolution, which began in the last half of the 18th century and saw the emergence of cast iron, wrought iron, and finally steel for bridges. So every time we talk about the history of bridges, every time we talk about the history of modern highway bridges, we usually start on the story of having a problem to on how to cross a small stream of a body of water, like for example a river. So before, when the bridges are were not already invented, when we encountered an obstacle like a small stream, and we want to cross that small stream from one side of the stream to the other, we usually use a log or a trunk of a tree for us to be able to traverse that small stream from the one side to the other. So before the invention of bridges, the bridges that we use were usually a log or a trunk of a tree. We are placing that log across the small stream, and then uh, that is where we uh, cross the small stream using that small log. Or usually, if we don't have a log, if we don't have a trunk of a tree, but there is an available vine that is suspended on very large on very large trees, we usually use them as well for us to be able to traverse a some obstacle on 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 a particular location, like again like a small stream. If you have a suspended vines there, we usually use that vine to swing back and forth to for us to be able to traverse that small stream. So that's usually where the history of bridges starts, to the use of a log, to the use of suspended vines as our way to traverse an obstacle. So that's where we usually start the history of bridges. And then after that, it is usually followed by the development of the stone arches that were attributed to the Roman engineers of the second and first centuries BC, as well as the beautiful bridges that were made across the Europe during the Renaissance period. So those were the development of the bridges that we have today started until the Industrial Revolution, which began in the last half of the 18th century, where they utilize the use of cast iron, wrought iron, and finally steel as a material to build a bridge. So usually when we talk about the history of bridges, those are the records that we usually talk about, starting from utilizing a log or a trunk of the tree or a vine suspended on a tree, to the stone arches of the Roman engineers, to the beautiful bridges across Europe during the Renaissance period, until the Industrial Revolution, where we already utilize the use of cast iron, wrought iron, and steel that we still use until this day. So just to have a quick look on the development of modern highway bridges, let us just have a quick look back on the bridges that we have through the years, starting from the stone arch bridges made by Roman engineers. So, stone arch bridges look something like this. So, stone arch bridges are obviously made out of stone that were shaped as an arch like this. The Roman bridge builders first come to mind when discussing stone arch bridges. They utilized the semicircular arch and built elegant and handsome aqueducts and bridges, many of which are still standing today. the stone arch has been around a long time and how its form was first discovered is unknown. But credit is due to the Roman engineers because they are the ones who saw the potential in the stone arch, uh, develop construction techniques, build foundations in moving rivers, and left us a heritage of engineering works that we marvel at today. So we usually attribute the development of stone arches or stone arch bridges to the Roman engineers who were the first ones who saw the potential to the use of stone arches as a material for a bridge structure. And and as you can see, until today, the stone arches or the stone arch bridges that were made by Roman engineers are still standing today. So you can see there how marvelous the structures that were made by the uh, engineers of long ago, because the structures that they had engineered before are still standing until today. Although at some point it's kind of ironic because today some of the bridges that we build today uh, usually usually have a shorter useful life compared to the bridges that were made long ago by people, by engineers who were not so modernized, who didn't have a modern technology to use to build their bridges at that particular time. It's kind of ironic, although we can still marvel on how the bridges of long ago were still standing until today. So another bridge that were made through the years are the wooden bridges like this on the picture. Early bridge builders began their careers as millwrights or carpenter mechanics. They had no clear conception of truss action, and their bridges were highly indeterminate combinations of arches and trusses. They learned from building large mills how to increase clear spans by using the king post system or truss beam. They also appreciated the arch form and its ability to carry loads in compression to the abutments. This compressive action was important because wood joints can transfer compression more efficiently than tension. So after the Roman engineers used stone arches as their bridge, the use of the use of wood uh, uh, were developed because most of the bridge builders before were actually carpenter mechanics. So most of the time, the material that were readily available for them, for the bridge builders of that day, are just wood or woods coming from trees. So with that available material, even with no clear conception of truss action, those bridge builders started to build wooden bridges that were made out of wood. So you can see here the materials or the members of the bridge were made out of wood. So these bridge builders of long ago uh, found the usefulness of wood in resisting compression more than the resistance of a wood on tension. So they utilize that ability of wood to resist more on compression forces than tension forces uh, by utilizing them as the members of the truss that will hold the bridges that they had built on that day. So the next uh, historical bridges through the years. The next bridge that were developed through the years was the or were the metal truss bridges like this one. Wooden bridges were serving the public well when the loads being carried were horse-drawn wagons and carriages. Then along came the railroads with their heavy loads, and the wooden bridges could not provide the necessary strength and stiffness for longer spans. As a result, wrought iron rods replaced wooden tension members, and a hybrid truss composed of a combination of wood and metal members was developed. As bridge builders' understanding of which members were carrying tension and which were carrying compression increased, cast iron replaced wooden compression members, thus completing the transition to an all-metal truss form. So the wooden bridges that were built before by bridge builders were actually good because the traffic that they were supposed to carry at that particular time were just horse-drawn wagons and carriages, or in other words, the traffic there that they were supposed to carry at that time were just lighter loads. So when the heavy loads such as the railroads came, the strength of the wooden bridges became inadequate to support those heavy loads like the railroads that you are seeing here, thereby forcing the bridge builders to utilize some other material which which were the metals that you are seeing here today. So what they did were as their knowledge about the uh, the tension and compression action of each member of the truss, they utilize that knowledge and replace the the wooden members of a wooden bridge, especially the tension members, into metal members. So they had replaced the members that were carrying tension forces into a metal member, since as we all know, metal uh, has a very good property in resisting tension forces. So that's what they had done before. They had uh, altered, they had changed the members of a truss bridge or a wooden bridge from wood to metal. And so at that time, they made a hybrid bridge composing of metal and woods. Although as their knowledge about the tension and compression action of each members increase, they also replace as well the members that were carrying compression. And until then, the transition from wooden bridge to an all metal truss bridge came into realization. So other bridge that came through the years are the suspension bridges. So suspension bridges look something like this. Actually, this bridge that you are seeing here is the famous Golden Gate Bridge located in San Francisco, USA. In previous suspension bridges, the roadway was flexible and followed the curve of the ropes or chains. By stiffening the roadway and making it level, James Finley, who was attributed as the inventor of modern suspension bridges, developed a suspension bridge that was suitable not only for footpaths and trails, but for roads with carriages and heavy wagons. So the early suspension bridges that were developed before were all were very flexible. Actually, the famous example of that flexible bridge that were built before is the Tacoma Bridge. So you can search Tacoma Bridge in the internet, and you can see that very flexible bridge that uh, that swings even if there is actually no traffic that that is traveling along that bridge, that Tacoma Bridge. So you can see that Tacoma Bridge is very flexible, and it swings back and forth even with no strong wind or even with no traffic that was traversing it, until such time that this flexibility became the cause of the sudden failure of this Tacoma Bridge. So this Tacoma Bridge is, this Tacoma Bridge was one of the failures in bridge engineering and bridge construction that left a very important lesson on bridge engineering itself. So nowadays, the modern suspension bridges like this one, the Golden Gate Bridges, were made as stiff as possible to prevent swinging, as, especially when there is a strong wind, so that the 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 roadway that is being carried by the suspension bridge will be more stable for uh, use of traffic. So the main load carrying member of a suspension bridge is this cables that you are seeing here. So these cables are connected to another cable which transfer the load of the roadway, the weight of the roadway, to uh, the main carrying post that you are seeing here. So that is again another kind of bridge that we had developed through the years. Another kind of bridge that were developed through the years were metal arch bridges such as this. Actually, this is Sydney Harbour Bridge that you can see on in Australia. This is Sydney Harbour Bridge in Australia. Arch bridges are aesthetically pleasing and can be economically competitive with other bridge types. Sometimes the arch can be above the deck, like this one. Other times, when the foundation materials can resist the truss, the arch is below the deck. So sometimes this arch that you are seeing here can be placed below the deck. So this is the deck where the vehicles pass to. So sometimes the arch that is supporting the deck can be placed above the deck or below the deck. Restraint conditions at the supports of an arch can be fixed or hinged, and if a designer chooses a third hinge can be placed at the crown, which is this point. The crown is the highest point on the arch. A third hinge can be placed at the crown to make the arch statically determinate or non-redundant. So you can see here that through the years, the 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 concept of arch bridges were utilized to develop what we now have as metal arch bridges such as this. So as we have seen on structural theory, on structural analysis, we have seen there that an arch uh, uh, has a very good strength in resisting axial forces. So that's why it's usually used as the main support of bridges, such as this, the Sydney Harbour bridges. And arch bridges, metal arch bridges, are not only utilized because of its strength, but also because of its given aesthetics. So usually, the arch bridges, metal arch bridges, give a pleasing appearance that that was the reason why it became popular in the modern highway bridge industry. Another bridge that were invented, another bridge that was invented through the years were reinforced concrete bridges like this one. In contrast to wood and metal, reinforced concrete has a relatively short history. It was in 1824 that Joseph Asdean of England was recognized for producing Portland cement by heating ground limestone and clay in a kiln. This cement was used to line tunnels under the Thames River because it was water resistant. Some concrete arches were built using the pre-stressing construction techniques first developed by the French engineer Ernest Freycinet in the 1920s. So another bridge that was developed through the years are reinforced concrete bridges like this one. So as the name suggests, the bridge is made up of reinforced concrete uh, which is reinforced by reinforcing steel. So usually we use pre-stress construction techniques to build reinforced concrete bridges, especially if the span of the bridge uh, is kinda long. So if we have a long span bridge, usually we incorporate pre-stressing construction techniques for us to be able to construct that long span reinforced concrete bridges. So last bridge that was developed through the years are girder bridges such as this one. So what are girder bridges? So technically girder bridges are just bridges being supported by girders. So these girders that support the deck of the bridge where the roadway uh, is placed can be made up of concrete or reinforced concrete or pre-stressed concrete or steel material. So that girder can be made up of pre-stressed concrete or reinforced concrete or just steel material. Some of the early girder bridges, with their multiple short spans and deep girders, were not very attractive. However, with the advent of prestressed concrete and the development of segmental construction, the spans of girder bridges have become longer and the girders more slender. The result is that the concrete girder bridge is not only functional but can also be designed to be aesthetically pleasing. So actually in our subject bridge engineering, especially the part of the bridge design, we will be focusing more on how to design bridges of this type, girder bridges which are supported by girder, either concrete bridges, either concrete girders or steel girders. So we will be focusing more on how to design bridges that are being supported by girders of this kind, either concrete girders or steel girders. Today's highway bridge is an offspring of the rapid development of the modern transportation network. The evolution from the design of new structures in almost assembly line fashion to the detailed design of a bridge rehabilitation did not occur overnight. Indeed, the creation of modern standards and specifications in place today is an outgrowth of the efforts of an entire generation of civil engineers who grew up professionally during the formative years of what was, and still is, the largest public works project in the history. So indeed, the modern highway bridges that we are using today did not occur overnight. Those techniques, those construction techniques, those standards, those specifications that we are using today to build modern highway bridges did not occur overnight. So actually, these are the result of the efforts of those engineers, starting from the non-technical people of long ago up to the Roman engineers, the early Roman engineers, up to the engineers that we have today. All of their efforts resulted to the bridge engineering that we have today. So the bridge engineering, the designs, the techniques in construction, in designing, the standards, the specifications that we are using today did not occur overnight. They are actually a result of the efforts of those professionals before our time that were forced to design and construct bridges with the little knowledge that they had. So we can see there that indeed bridges, the modern highway bridges, uh, indeed took a long time to develop and to be on where it is today. So, if you want to know more about the history of bridges, you can check out these links that I have provided here. You can check out this link, Engineering History, Bridges, and then this, the history of bridges, and lastly, this, the history of bridge construction. So, if you want to know more about the history of bridge engineering, you can check these links that I have provided here. So we are now done addressing our third goal, which is for you to be able to state the origins of the modern highway bridge. So now we will move on addressing our second to the last goal for this discussion, which is for you to be able to define the different terms used in bridge engineering, especially the different parts of a bridge. So without further ado, let us start addressing our fourth goal. So before we move on to studying bridge engineering, we will eventually encounter some terms, some bridge engineering terms that might be new to our ears. So before moving on studying bridge engineering, it is worth it is worth our time to familiarize ourselves to this bridge engineering terms like the highway bridge site. So what do we mean when we say highway bridge site? So it is just a complicated place and the point where a suite of civil engineering disciplines converge. So this is the uh, main topic of our engineering. This is the reason why we are engineering, which is because of the highway bridge site, because we have a highway bridge site. So this is where our engineering skills are being applied to. So that is one term that we will encounter as we move on studying bridge engineering. Other terms that we will encounter are the concerns of a bridge designer. So when a bridge designer designs a bridge, he or she is concerned with the highway design for the overpass and underpass alignment and geometry. So that is one of the concerns of a bridge designer, the highway design, the whole design of the highway, their alignment and geometry, what must be the required width, the required length of the highway. So that particular part of that particular part of the design is actually one of the concerns of a bridge and bridge designer. Another concern of a bridge designer is the structural design for the superstructure and substructure elements. So later on, we will define the meaning of superstructure and substructure elements. But as of now, we will just state that a bridge designer is actually concerned with the structural design of the superstructure and substructure elements, meaning the bridge designer is concerned on providing adequate strength for the superstructure and substructure for them to be able to resist or to carry the intended loads that we anticipate that our bridge will be carrying. So the bridge designer must provide a structural design that will provide adequate strength to resist the the expected volume of traffic that will use our bridge that we are designing. Another concern of a bridge designer is the geotechnical engineering for the pier and abutment foundations. So not only the structural design of the superstructure and substructure is the concern of the bridge designer. The bridge designer is also concerned with the uh, providing enough strength for the supporting soil. So the bridge designer must be able to design as well the bridge designer must engineer as well the soil the supporting soil that will actually support the whole structure, the whole bridge. So the geotechnical engineering part of the design of bridges is also a concern of a bridge designer. He or she must also provide uh, enough or adequate strength for the soil, for the supporting soil, for it to be able to carry the whole bridge, the whole superstructure together with the substructure. Another concern of a bridge designer is the hydrology and hydraulics for proper bridge span length and drainage of bridge site. So the bridge designer must also ensure that there will be no ponding along the bridge, because if there will be a ponding of water on the bridge, it might be it might be an additional load that must be carried by the bridge. And if the bridge has no proper drainage, ponding of water might occur. So therefore, a bridge designer must also provide adequate drainage for the bridge site. He or she must ensure that there will be no ponding of water, so that there will be no additional load to be carried by our bridge structure. Last concern of a bridge designer is the surveying and mapping for the layout and grading of a proposed site. Of course, before the construction begins, layout and grading of the proposed site must be provided first, because this will be the guide of the whole construction process for us to be able to construct the bridge, the highway bridge site properly. So there must be surveying and mapping first for the proper alignment and layout and grading of our proposed site. So another term that we will encounter later on as we study bridge engineering is the word crossing or underpass. So these are just human-made, like highways, rail lines, or canals, or natural crossing like watercourses. So the crossing or underpass are actually the reason why we are building a bridge. These are actually the reason why we are building a bridge over them. These are the man-made obstacles or natural obstacles that we want to traverse or to cross. That's why we usually build a bridge. So this can be man-made obstacles like highways, rail lines, or canals, or natural obstacles such as rivers or any body of water. So we are building bridge over this crossing or underpass for us to be able to easily traverse this crossing or underpass. We are building a bridge for us to be able to easily traverse this underpass or crossing. Another term that we will encounter later on as we study bridge engineering is the word span. So what do we mean when we say span? Span is a segment of a bridge from support to support, like this one. If you can see this background of our PowerPoint, this is actually the San Juanico Bridge. And if you can see here, this is actually one of the support of the San Juanico Bridge. So the other support can be found somewhere here. So the part of the bridge starting from one support to the other support is actually what we call the span. That is the segment of a bridge from support to support. So the other terms that we will be encountering as we study bridge engineering are the different parts of a bridge. So we can see later on the terms used to indicate the different parts of a bridge. So a bridge, the different parts of a bridge looks something like this, or in actual, uh, the different parts of a bridge can be look like this. So what are the different parts of a bridge? So actually, these figures or these photos or GIF that you are seeing uh, uh, already has the most common part of every bridge. So what are the most common part of a bridge? So the first one, the first part of a bridge that is always present on every bridge is the deck. So this is the deck here, or in this figure, this is the deck, the black one. The part of the bridge where the traffic, the vehicles travel. So that is what we call the deck. And then the part of the bridge that supports the deck is actually what we call girder. If the if the bridge is a girder type bridge like this one, like what you are seeing here on your in the figure, because there are actually different type of bridges that we will study later on our when we will be addressing our fifth goal for this discussion. So these are the girders. These are the part of the bridge that supports the deck. So the other part of a bridge that actually usually uh, put below the interface of the girder and the pier is what we call the bearing. So these are actually part of the bridge that are put below the interface of the girder and the pier. So usually these are put to properly distribute the loads or the force that is being transferred by the girder to the supporting pier. So the other part of the bridge that where the bearing rests is what we call the pier. So there are actually different types of pier that we will study later on. So the pier is look something like this or this. So there are actually different types of pier that we will study later on. So the pier is the part of the bridge that supports the bearing together with the girder and the deck. And the other part of the bridge that supports everything, the pier, the bearing, the deck, and the girder, is what we call the footing. So this is the footing. So the footing can be actually shallow footing or deep footing depending on the quality of the soil on the highway bridge site. So these are actually the most common part of a bridge. Although there is actually a general term for these different parts of a bridge. So there is a general term for these different parts of a bridge that we have to familiarize ourselves. So these general terms, we will start studying these general terms on the word superstructure. So what do we mean when we say superstructure? Superstructure is the general term that we use to describe the components, all of the components of a bridge above the supports. So all of the bridge, all of the parts of the bridge, all of the components of a bridge, all of the components of a bridge, starting from the girder above, that is what we call the superstructure, the part of the bridge that is being supported by the supports. So we call them superstructure, parts or components of a bridge above the supports. So there are different basic superstructure components. Just like what I've said before, superstructure is a general term. So the superstructure describes these basic components that I will enumerate here. So the first one is the wearing surface or course. So what is a wearing surface or course? It is that portion of the deck cross-section that resists traffic wear. In some instances, this is a separate layer made of bituminous material, whereas in some other cases, it is an integral part of concrete deck. So where is the wearing surface? This is actually the wearing surface. It is the layer of the road that is put on top of the deck. So this is the deck. and we usually put another layer on top of the deck where the traffic, the vehicles travel. So if you can see this San Juanico Bridge on the background, the wearing surface is actually this, where this is actually the roadway that is being traversed by the traffic or the vehicles. So this wearing surface can be integrated on the deck, or sometimes or most of the time they are just put as another layer made up of bituminous material like asphalt. So that is one component of the superstructure, the wearing surface. Another component, another basic component of superstructure is the deck. So in this drawing, you can see the deck here. So this is the deck. So what is a deck? Deck is the physical extension of the roadway across the obstruction to be bridged. It can be a reinforced concrete slab. In an orthotropic deck bridge, the deck is a stiffened steel plate. The main function of the deck is to distribute loads transversely along the bridge cross-section. The deck either rests on or is integrated with the frame or other structural system designed to distribute loads longitudinally along the length of the bridge. So the deck is actually this part of the bridge where the wearing surface is put on top of it. So sometimes the deck is integrated with the supporting girders. If the bridge is a girder type bridge, sometimes it is integrated. It is built integrally with the girder supports, but sometimes uh, it is constructed separately and just put on top of the supporting girders. So this deck is actually the extension of the roadway that is being connected by the bridge. So you can see on the end of the bridge, there is actually a roadway that is being connected by the bridge to the other roadway on the other side. So that part of the bridge that connects the roadway from one side to the other is actually what we call the deck. Another basic component of a superstructure is the primary members, or are the primary members. So the primary members distribute loads longitudinally and are usually designed principally to resist flexure and shear. Beam type primary members such as shown are also called stringers or girders. A small fillet or haunch can be placed between the deck slab and the top flange of the girder to adjust the geometry between the stringer and the finished deck. So on this drawing, you can see the primary members are this. So these primary members, if the bridge is a girder type bridge, we usually call this primary members as stringers. So in actual, primary members or stringers or girders, simply girders, look something like this. So these are the longitudinal component of a bridge, which have a main purpose of resisting flexure and shear. So actually, these are the part of the bridge that supports the deck together with the wearing surface. That is the part of the bridge where the deck is put on top. So as you can see here, sometimes we are putting a small space, which is what we call a haunch between the deck and the top of the girder or the stringer, so that we can easily adjust the geometry between the deck and the girder. Because sometimes, especially if the bridge is with a curvature shape, sometimes we need to super elevate the the deck itself. So we need to incline the deck, especially if the part of the bridge is in curvature, so that we can easily adjust the geometry between the deck and the girder. We can easily adjust the super elevation. We can easily elevate or incline the deck if we will put a haunch between the deck and the top of the supporting girder or primary member or stringers. So another basic component of a superstructure is the secondary members, which are bracing between primary members designed to resist cross-sectional deformation of the superstructure frame and help distribute part of the vertical load between stringers. They are also used for the stability of the structure during construction. Secondary members composed of horizontal cross frames or lateral bracing at the top or bottom flange of a stringer are used to resist lateral deformation. In curved girder bridges, the diaphragms are considered primary members because they are load-carrying members that help resist torsion caused by vertical loads. So the secondary members are the members that are placed in transverse direction with respect to the longitudinal members, which are the primary members or stringer. So in this drawing, you can see these members here that are put in transverse direction with respect to the longitudinal girder, and these are what we call the secondary member or the diaphragm. Or if you will look on this actual drawing or actual picture, these are the secondary member or diaphragm. So their main purpose is to resist lateral deformation or lateral loads, and they are also used to add additional stability to the whole structure during construction. So that is the secondary members. So those are the basic components of a superstructure: the wearing surface, the deck, the primary member, and the secondary member. So these are the parts of the bridge that is being supported by the substructure. That is, again, another general term used to describe those parts of a bridge that are being used to support the superstructure. So the other general term that we will be encountering as we study bridge engineering is the word substructure. So what do we mean when we say substructure? So substructure is actually the term we use to describe all of the elements required to support the superstructure. Or in other words, these are the components or elements of a bridge that are located below the superstructure. These are the elements that are used to support the superstructure. So just like the superstructure, substructure also has its basic components. So these are the parts or elements of a bridge that comprise the substructure. So the first one is the abutments. Abutments are earth-retaining structures that support the superstructure at the beginning and end of a bridge. Like a retaining wall, the abutments resist the longitudinal forces of the earth underneath the overpass roadway. So abutments are actually almost the same as piers, but the only difference is piers are located on intermediate points between abutments, while abutments are located only at the beginning and at the end of a bridge. So those are the abutments. Again, abutments are those support of a bridge that are usually located at the beginning and at the end of a bridge, while the piers are the supporting structure or the supporting part of a substructure that are located in between abutments or in intermediate points between abutments. So usually abutments are used to retain earth because usually the beginning and the end of a bridge usually has earth to be retained so that our bridge will can have stability. So that part of the bridge, that part or component of a substructure that is usually located at the beginning and the end of a bridge, that is usually used to retain the earth beneath the beginning and the end of a bridge, is what we call abutment. So they usually act like a retaining wall. So the longitudinal longitudinal they retain the longitudinal force exerted by the earth underneath the overpass roadway. So the other component of a substructure is what we call the pier. So piers, just like abutments, piers are structures that support the superstructure at intermediate points between the end supports or the abutment. So this is what I am saying a while ago. Piers are actually almost the same as the abutments, but they are just usually placed in intermediate points or in between abutments. Abutments are usually placed at the beginning and the end of a bridge to retain earth, while piers are located in between these abutments. The physical conditions of the bridge site play an important role in deciding which type of pier to use. For example, to provide a large clearance makes a hammerhead attractive, while solid wall are well suited for shallow water crossings. So there are actually different types of pier, and this and deciding which type of pier to be used on a particular highway bridge site is actually dependent on the advantages of using that particular pier on that particular highway bridge site. So one example of a pier or pier type is actually this. This is what we call hammerhead pier. So this is the hammerhead pier. So hammerhead pier or hammerhead piers are usually used whenever we want to have a a large clearance underneath the superstructure. So you can usually see this type of pier on locations like the 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 supporting pier a of our light rail transits here in the Philippines. So if you can notice, some of the piers used to support the superstructure of LRT, LRT1, LRT2 are actually hammerhead type pier. So why is that? Why do we use hammerhead type pier on those locations? So that we will still have a large clearance, a large space beneath the superstructure so that traffic can still flow beneath the superstructure. So that's one advantage of using a hammerhead pier. Another type of pier is what we call a solid wall or gravity pier. So this is what a solid wall or gravity pier looks like. So we usually use solid wall or gravity piers uh, whenever we have a bridge constructed on a shallow water crossing. So this type of pier are usually suited for bridges that are constructed on shallow water crossings. Another type of pier is what we call column bent pier. So these are the column bent pier. So it is just like you are having a very large column supporting the superstructure. So that is what we call the column bent pier. So the same as the hammerhead, the same as the advantage of using the hammerhead pier, we also use column bent pier so that we will still have a clearance, large clearance beneath the superstructure so that traffic can still flow along the direction of the bridge. So that we can still have a clear space here beneath the superstructure. That's why we usually use column bent pier. So if you already seen one column bent pier here in the Philippines, we usually use this for skyways. So we usually use column bent pier on skyway bridges so that we will still have a clear space beneath the superstructure. So the traffic volume, the traffic can still flow beneath the superstructure. Another component of a substructure are the bearings. So bearings are mechanical systems that transmit the vertical and horizontal loads of the superstructure to the substructure and accommodate movements between the superstructure and the substructure. Bearings allowing both rotation and longitudinal translation are called expansion bearings, and those that allow rotation only are called fixed bearings. So bearings look like this. So this is actually what we call bearing. Bearing or bearings are usually placed on the interface of the girder support or the primary member and the supporting substructure. So that is usually placed on their interface with the purpose of transmitting the vertical and horizontal loads from the superstructure to the supporting substructure. And another purpose of putting a bearing is to accommodate movements between the superstructure and the substructure so that there will be less stress that will be generated whenever there is a relative movement between the superstructure and the substructure. So that's why we are putting a bearing in between them so that whenever there is a relative movement between them, there is no additional stress that will be generated between the interface of the superstructure and the substructure. So bearings that allow both rotation and longitudinal translation are called expansion bearings, while those which allow rotation only are called fixed bearings. So another component of substructure is what we call pedestal. Pedestal is a short column on an abutment or pier under a bearing that directly supports a superstructure primary member. The term bridge seat is also used to refer to the top surface of the pedestal. So pedestal is actually just a short column on an abutment or pier under a bearing. So usually bearings are put above the pedestal, or in other words, pedestal supports the bearing. So the purpose of the pedestal is to, just like the bearing, the purpose of the pedestal is to actually distribute the load or the loads that is being transferred from the superstructure to the substructure. So that's one purpose of the pedestal, to evenly distribute the load transfer so that there will be less stress that will be produced on the interface of the substructure and the superstructure. Another component of a substructure is the stem. So stem is a primary component of the abutment above the footing, supporting pedestals. Its main function is to transfer loads from the superstructure to the foundation. So you can find stem on abutments. So again, take note, abutments are those pier-like part of the substructure that can only be found in the beginning and the end of a bridge. So you can find stem on that particular location. So stem usually supports pedestals. So its main function is again to, just like the pier and the abutment, its main function is to transfer loads from the superstructure to the supporting foundation. Another component of the substructure is the backwall. Backwall is the component of the abutment acting as a retaining structure on top of the stem. It also supports an approach slab if there is one. So later on, we will define what do we mean when we say approach slab. So, but at this point in time, let us focus on the back wall. So what do we mean? What is a back wall? So back wall is again a component of the substructure that can only be found on the abutment. So again, I'll repeat, abutment or abutments can be found only in the beginning and in the end of a bridge. So abutment are usually used to retain the earth on the end, in the end, and in the beginning of a bridge. And in addition to that support, in addition to that abutment, usually we usually have also back wall or back walls with the purpose the same as the abutment, which is to retain uh, retain to act as a retaining structure on top of the stem. So we usually place back wall on top of the stem. And another purpose of back wall is to support the approach slab. So when we say approach slab, although we will define it again later on, when we say approach slab, this is actually the very short slab that is used to connect the roadway and the bridge itself. So that very short slab is usually supported by the back wall. Another component of a substructure is what we call the wing wall. So wing wall actually looks something like this. So this is the wing wall. So if you can see here on the figure or the picture, the wing wall looks actually like a wing. So this is the triangular shape here. So wing wall is a side wall to the abutment back wall and stem designed to assist in confining earth behind the abutment. Wing walls may be designed parallel to the bridge and approaches, or they may have a skew angle, just like this. So the wing wall that we have here on this photo is actually constructed with a skew angle. So what is the purpose of a wing wall? The purpose of the wing wall is the same as the purpose of the back wall and the abutment, which is to retain the earth behind the abutment. So it is again an additional assistance, an additional support to retain the earth beneath or behind the abutment. So you can usually find wing walls on expressways. So if you had already traveled on expressways like NLEX or SLEX, you can find these wing walls on those part of the expressways where there is a actually a bridge built over the expressway itself. So you can find those wing walls on expressways usually. Another component of a substructure, which is actually a major part of the substructure, is what we call the footing or footings. So footings transfer loads from the substructure to the subsoil or piles. A footing supported by soil or bedrock without piles is called a spread footing. A footing supported by piles is known as a pile cap. Foundations supported by piles are also called deep foundations. So footings are one of the most important part of the substructure because simply because it is the part of the substructure, it is the component of the substructure that actually transfer the loads from the substructure itself to the supporting soil. Actually, when the footing is actually the one that transfers the loads from the substructure to the supporting subsoil, it is usually called a spread footing. If it is the one uh, who directly transfer the loads from the substructure to the supporting soil, it is called a spread footing or a shallow foundation. Although sometimes uh, the supporting soil has a very low or no, sometimes the supporting soil has a not so good quality, like it has a very low shear strength or bearing strength, or in other words, the soil is has a very low quality. Sometimes the supporting soil has a very low quality in resisting or supporting a structure. So sometimes a shallow foundation or a spread footing is not advantageous to use on that particular soil with low quality of strength, with low strength soil. So on those cases, we usually use uh, deep foundations, such as putting a pile. So a pile is the a pile or piles are used when the soil under a footing cannot provide adequate support for the substructure. in terms of bearing capacity, overall stability, or settlement, which extend down from the footing to a stronger soil layer or to bedrock. There are a variety of types of piles ranging from concrete, which is cast in place, also called drilled shafts or caissons, or precast to steel edge section piles. Just like what I'm saying before, sometimes the supporting soil of a particular highway bridge site has a very low strength in terms of bearing strength or shear strength, or in other words, it has a very low quality. So on those cases, shallow foundations or spread footings are not advantageous to be used. So sometimes we are using what we call deep foundations, wherein we are using piles that are actually extended down uh, on the in the bottom of the earth until it reach a very strong soil layer or bedrock. So these piles are connected to the footing. So when the footing is actually used in the foundation, it is actually called pile cap. So that pile cap or simply footing that is used in the foundation is where the piles are inserted. So that the foundation looks something like this on the picture. So you can see here the footing or the pile cap and the pile. So the pile are simply looks like a very long column that is embedded deep beneath the earth. It is actually extended deep beneath the earth until it reaches a very strong soil layer or bedrock, and wherein it can transfer the load or the loads that is or that are being carried by the substructure. So we usually use piles, the foundations, on soil site. I mean on highway bridge sites that have a not so good quality of soil. So we usually use those the foundations on those highway bridge sites that have a not so good quality of soil. So in which case, shallow foundations or spread footings are not advantageous to be used. So those are the uh, piles. That is what a pile looks like. And then again, that part of the foundation, that's that rectangular part, is again what we call the footing or the pile cap. So again, we usually call footing a pile cap whenever we use it in deep foundations, whenever we insert a pile on it. So the last component of substructure that we will study is the the word or the term sheeting. So what do we mean? What is this component of a substructure, which is the sheeting? What do we mean of sheeting? Sheeting is the vertical planks that are driven into the ground to act as a temporary retaining walls, permitting excavation in coffer dams or shallow excavation. So what does a sheeting looks like? So sheeting looks like this. So this is what we call sheeting. So sheeting are actually just composed of vertical planks, several vertical planks that are interweaved together to form an enclosed space. So usually in actual construction, in order for us to provide a temporary retaining wall, especially on construction projects that are located on bodies of water, we usually uh, conduct what we call sheeting, wherein we insert a vertical plank, several series of vertical planks uh, deep beneath the earth, beneath the water surface, and then until we have an, an enclosed space. We insert series of vertical planks beneath the earth, beneath the water surface, until we have an enclosed surface like this one. So until then, uh, when we already have a or an enclosed space like this one, what we do is excavation of the earth beneath the water surface can already be started, as well as the drainage of the water inside the enclosed space made by the sheeting. So this is how we usually construct the foundations of bridges that are located on bodies of water. We usually insert their sheeting, which acts as a temporary retaining wall. Usually insert it or insert them deep beneath the earth to form an enclosed space. So when we already have a or an enclosed space, what we do is we excavate the earth enclosed by that sheeting together with the water that is also enclosed on that enclosed space formed by the sheeting. So in that way, we can already start excavation and the foundation works. We can already start or commence the foundation works for the support or the substructure of a particular bridge that is located usually on a body of water. So that is sheeting. Actually, this construction or activity or operation that you are seeing here is what we call coffer dam. This is what coffer dams should look like. So coffer dams are actually this enclosed space that are usually used for foundation works on bodies of water. So you can also find sheeting sometimes on the sides of a river. So one another purpose of these sheetings is to retain uh, is to act as a retaining wall. That's why we usually also use this on the sides of a river so that we can retain the soil on the side of the river. So on the side of the river so that these soils will be retained, this earth will be retained and will prevent erosion on the river. So those are some of the basic components of a substructure. So those are the terms that we will encounter later on as we study bridge engineering. So another general term that is used to describe the different parts of a bridge are what we call appurtenances and site-related features. So what are these? What are appurtenances? Appurtenance is any part of the bridge or bridge site that is not a major structural component yet serves some purpose in the overall functionality of the structure, such as guardrail. So this appurtenances or appurtenance is actually those part of a bridge that actually don't have a major role on supporting the whole bridge structure, but still they serve some purpose in the overall functionality of the structure, such as a guardrail. So in other words, appurtenances are just like an accessory to the bridge. So these are just the major appurtenances and site-related features that can be found in every bridge. The slope that tapers from the abutment to the underpass or embankment is covered with a material called slope protection, which should both be aesthetically pleasing and provide for proper drainage and erosion control. For waterway crossings, large stones, also called riprap, are usually used for slope protection and foundation score protection. So slope protection looks something like this. So slope protection is being provided to prevent erosion of soil, or in other words, it is provided for erosion control. So this is what we call the slope protection. So when sometimes the slope protection that is being used for waterway crossing is usually made up of large stones, and when that slope protection is made up of large stones, it is usually called a riprap. So this riprap is a slope protection that is usually used on waterway crossings. So that is one of the appurtenances or site-related feature that can be found in a bridge. Another appurtenance another appurtenance or site-related feature that can be found in a bridge is an underdrain. In order to provide for proper drainage of a major substructure element such as an abutment, it is often necessary to install an underdrain, which is a drainage system made of perforated pipe or other suitable conduit that transports runoff away from the structure and into appropriate drainage channels, either natural or human-made. So under drains look something like this. So the purpose of putting an under drain on every substructure of our bridge is to prevent the storage of water behind the substructure. So that's one purpose of putting an under drain on the substructure of our bridge, to prevent the storage of water behind the substructure. So why is that? What will happen if we will have a water that will be being stored behind our substructure? So the tendency will be that stored water will will exert an additional pressure to our substructure that can eventually result to failure of our substructure if our substructure is not properly designed to resist an additional load coming from the water pressure that will be exerted on it if there will be a water that will be stored behind our substructure. So in order to prevent the storage of water behind our substructure, we usually put under drains like this, composed of perforated pipes or drain holes, so that water will not be stored behind our substructure. So what will happen if we will provide under drain or under drains is the water will be diverted using those under drains away from our substructure, so that this water will not be stagnant behind our substructure and eventually and consequently will prevent it from putting additional pressure on our substructure. So these perforated pipes composed of a pipe that has a series of holes along its length. These perforated pipes will will collect this stored water and eventually divert it away from our substructure. So it will divert the water away from our substructure to drainage channels, either natural drainage channels or human-made channels. So natural drainage channels are those like rivers or any body of water, or even directly to the sea. So that perforated pipe can divert the water behind our substructure away from our substructure directly to directly out of the sea or any body of water. So other type of under drain that is usually used in a substructure are drain holes. So it serves the same purpose as the perforated pipe. So in order for the water to be not stagnant behind our substructure, we usually put a drain hole through our substructure so that water will seep out of that drain hole, and as a result, there will be no water pressure that will be developed behind our substructure, and eventually will prevent uh, substructure collapse or failure, since there will be no water pressure that will be developed behind our substructure. So those are under. drain. That is again another appurtenance or site-related feature that can be found on any bridge. The section of overpass roadway that leads up to and away from the bridge abutments is called the approach or approach roadway. To compensate for potential differential settlement at the approaches, a reinforced concrete slab or approach slab is sometimes used for a given distance back from the abutment. The approach slab helps to evenly distribute traffic loads on the soil behind the abutment to eliminate the horizontal live load soil surcharge against the abutment, and to minimize differential settlement between the abutment and the approach roadway. An approach slab is typically supported by the abutment at one end and supported by the soil along its length. So this is again another appurtenance or site-related feature that can be found in a bridge. This is what we call the approach slab. So this this short slab that you are seeing here is what we call approach slab, and this part here is what we call the abutment, and this part here is what we call the approach roadway. So as you can see on the figure or on the GIF, the approach slab is that slab that connects the abutment to the approach roadway. So one reason or one purpose of this approach slab is to evenly distribute traffic loads on the soil behind the abutment. So that's one part of purpose of the slab, to evenly distribute these loads, the traffic loads, the vehicle loads that is being supported by the approach slab evenly beneath the soil. So it distributes the traffic loads evenly on the supporting soil behind the abutment. So that's one purpose of the approach lab. Another purpose of the approach lab is to minimize differential settlement between the abutment and the approach roadway, because as the traffic uh, travels along the approach roadway to the bridge, sometimes there will be a settlement that will happen on the abutment as well as on the roadway. So in order to prevent differential or different amount of settlement between the abutment and the approach roadway, we usually put approach slab, so that again to minimize the the settlement, the differential settlement between the abutment and the approach roadway. So as you can see on the figure or on the GIF, approach slab is usually supported by the abutment on its one end, and it is supported by the supporting soil along its length. So that is evident on this particular figure that you are seeing here. So that approach slab is usually located on both ends of a bridge, as the bridge connects the uh, as the bridge is being connected to the approach roadway. We usually provide the approach slab several uh, distance away from the abutment to connect the bridge itself to the approach roadway. So that is an approach slab. That is what an approach slab looks like. So that is again another appurtenance or site-related feature that can be found in a bridge. Another appurtenance or site-related feature that can be found in a bridge are bridge barriers. And traffic barriers. So what are bridge and traffic barriers? Bridge barriers are provided to restrain vehicles from crashing off the side of a bridge, and traffic barriers are protective devices used to shield motorists from obstacles or slope located along either side of a roadway. So what do bridge barriers look like? So this is a bridge barrier. So you can see bridge barrier on either side of a bridge with the purpose of preventing the vehicles from crashing off away from the bridge itself. So that is the bridge barrier, the feature that you are seeing on the side of every bridge. And the traffic barrier is look something like this. This is an example of a traffic barrier. Traffic barrier serves different purposes. Sometimes traffic barrier are used to divide the bridge or the road into several lanes. Sometimes it is used to prevent vehicles or the traffic from crossing one lane to the other. And sometimes traffic barrier is used to shield motorists from obstacles or slope located along either side of a roadway. Say for example, if there is a construction uh, or I mean if there is a construction activity happening on one side of the roadway, sometimes we use traffic barrier so that the traffic or the vehicles that are using the bridge will be prevented from crashing of that construction site on the particular bridge that we are concerned. So those are the bridge barrier and traffic barrier. Those are the appurtenances and site-related features that can be found in a bridge. So these appurtenances and site-related features are not actually part of the structural component of the bridge. They usually don't play a vital role on supporting the whole bridge, but still they serve some purpose in the overall functionality of the structure or the bridge structure. So another general term that is used to describe a part or parts of a bridge is what we call these miscellaneous terms. So before we start on engineering a bridge, it's worth it to know first, it's worth it to familiarize ourselves first on these miscellaneous terms. So the first of the miscellaneous terms that we will study is the vertical clearance. So what is a vertical clearance? Vertical clearance is the minimum distance between the structure and the highway underneath, such as this. So this is the vertical clearance. So usually we provide vertical clearance whenever we build a bridge over a highway. So there is a highway underneath a bridge. So on those cases, we usually provide vertical clearance such as this, the distance between the highway and the soffit or the bottom of the bridge. So the purpose of having a vertical clearance is to allow the traffic or the vehicle to underneath the bridge, to allow the vehicle or traffic underneath the bridge to safely travel underneath the bridge to provide adequate space, especially those vehicles of greater or great heights, to allow them to safely travel underneath a bridge so that there will be an adequate space for them to safely travel beneath a certain bridge. So that is the purpose of having a vertical clearance. So usually you can see vertical clearances on structures such as this or in tunnels. Whenever you traverse a tunnel, you can also find this. And any roads or highway that has a vertical limitation. So we usually provide a vertical clearance. So another miscellaneous term that describes a part of a bridge is what we call or what we call dead loads. Dead loads are permanent loads placed on a structure due to gravity of the structural and non-structural elements. So these dead loads are actually part of the bridge that are uh, actually fixed in position. So some example of dead loads are the weight of the bridge itself, the weight of the components of the bridge itself, like the weight of the deck, the weight of the girders or the primary members or the secondary members, the weight of the piers, the weight of the footings, etc., etc. So those are some example of the dead loads that are that comprise the bridge itself. So again, dead loads are those loads that are permanent, meaning these are the loads that are being carried by our bridge that are fixed in position. So that is the keyword there to define dead loads. There are loads that are fixed in position, meaning their position don't vary with respect to time. So another miscellaneous term that we must study is the superimposed dead loads. So these superimposed dead loads are dead loads placed on the structure after the concrete deck has hardened, like the bridge railing, the sidewalks, the wearing surface, etc. So superimposed dead loads are actually still dead loads, but the main difference is these superimposed dead loads are dead loads that are placed over our structure, over our bridge, after the concrete deck has hardened. Or in other word, in other words, these are dead loads that are just placed on top of our structure. So they are not integrally part of our structure or bridge, but they are just placed over our structure or bridge. So that's the main difference between superimposed dead loads and dead loads. Dead loads are those loads that are being carried by our structure, by our bridge, that are integrally part of our structure. While superimposed dead loads are those dead loads that are just placed on top of our structure or bridge after the concrete deck has hardened. So some examples of superimposed dead loads are bridge railings, sidewalks, and wearing surface. Another miscellaneous term to define a part of a bridge are live loads. Live loads are temporary loads placed on the structure such as vehicles, pedestrians, etc. So the main the key word to define live loads is these are the loads that are being carried by our bridge, by our structure, that has varying magnitudes and varying positions. Or in other words, they are not permanent in position with respect to our structure, with respect to our bridge. So some example of live loads that are being carried by our bridge or by our structure are vehicles. So obviously vehicles change in position as it travels our bridge, our roadway, obviously. So therefore, they can be considered as live loads because, as we defined a while ago, that live loads are loads that are being carried by by our structure that are not permanent, that have that has or that have not uh, that have no permanent position. Sorry. So these live loads are those loads that are being carried by our bridge, by our structure, that have no permanent position or no permanent magnitude. So one example of that uh, is a vehicle traveling along our bridge or a pedestrian traveling our bridge. Obviously, they are not part of our bridge. They are using our bridge, but they are not fixed in position. Their position vary with respect to time. So if they don't have a fixed magnitude and fixed position, therefore, we can consider them as a live load. Another miscellaneous term for us to be familiar is load rating. Load rating is an analysis of a structure to compute the maximum allowable loads that can be carried across a bridge. So this load rating are actually those signs that you can see when you enter a particular bridge. Like, for example, there is a signage there that says 10 tons. So that means that the maximum allowable load or weight that can use that particular bridge uh, is up to 10 tons only. So those vehicles that have a weight over 10 tons, they cannot use that particular bridge. So that 10 tons, that signage that we usually use when we enter a bridge is what we call the load rating. So this rating uh, is actually found by the analysis of the structure, by the analysis of a bridge. So we usually analyze a bridge, we usually design it in order for us to know what maximum load can it accommodate. So usually we are doing this on bridges or structures that are old, that are already old, because as we all know, the strength of a bridge, the strength of a structure deteriorates as time goes by. So therefore, we must continually analyze it in order for us to know the reserve or the available strength that it still have, so that failure of that particular bridge or particular structure will be prevented. Another miscellaneous term that we must be familiar with is the sheeted pit. So this term actually we already found uh, an overview of this particular term here, the sheeted pit. So this is actually similar to the term that we have described a while ago, which is the sheeting. So what is a sheeted pit? So a sheeted pit is a temporary box structure with only four sides that can be used as an earth support system in uh, in excavation for substructure foundations. The bracing elements used inside a sheeted pit to keep all four sides rigid are called wales, which run along the inside walls of the sheet piling, and struts, which run between the walls. When this type of structure is used where the ground level is below water, the sheeted pit is called a cofferdam. So as I've said before, we already had an overview of the definition of sheeted pit when we describe sheeting on the substructure component. So sheeted pit looks like this. So we usually use this sheeted pit as a temporary box structure to prevent uh, erosion of earth to the excavation. So we usually use this for excavation works to prevent the surrounding soil from eroding to the excavation. So this is still composed of vertical planks interweaved together and then provided by additional supports, which are called wales. So these are the wales, and struts. So this is the strut. So the wales run along the side or the inside walls of the sheet piling, and the struts run between the walls. So the wales are the ones that holds the vertical planks together, while the struts prevent the 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 vertical planks from eroding as it supports the earth beneath it. So if this sheeted pit is used on locations where the ground level is below water, the sheeted pit is called a cover dam, just like what we have seen a while ago on the sheeting term on the substructure part of our discussion. So you have seen there that the vertical planks are used on a ground below the water. So that is what we call a coffer dam. We usually use that in order for us to be able to construct the foundations of a bridge that is being constructed in a body of water. So last miscellaneous term that we must be familiar is the stage construction. Stage construction is a construction that occurs in phases, usually to permit the flow of traffic through a construction site. An example would be a bridge replacement project where one half of the structure is removed and replaced while traffic continues over the remaining portion of the structure. So when we say stage construction, this is just a construction that occurs in phases with the purpose of not preventing the flow of traffic. So its main purpose is to prevent the stoppage of the flow of traffic, even if we are having a construction activity. So one obvious or one famous, should I say one noticeable example of stage construction is whenever our local agency, our local public works agency, fixes our roads. So as you notice, whenever our local agency or local public works agency fix our roads, they usually don't do it on the whole road. They usually do the construction works on only half of the road in order for the traffic to still flow on the other half. So after they are done constructing, paving the road on one side of the road or the highway or the road, after they are done paving the road, the half of the after they are done paving half of the road, they will now start constructing on the other side of the road so that the traffic will now flow on the side of the road that is already finished. So that particular way of constructing is actually what we call stage construction. Construction that occurs in phases not uh, with the main purpose of preventing the stoppage of traffic flow. So those are the miscellaneous terms that we must be familiar before we start our study of bridge engineering. So we are now done addressing our fourth goal, which is for you to be able to define the different terms used in bridge engineering, especially the different parts of a bridge. So we are now down to our last goal for this discussion, which is for you to be able to define the different structure types used in bridge construction. So in actual bridge construction, actually there is a number of different bridge structure types that are usually used depending uh, on where exactly it will be constructed. So a wide variety of structures are in use for a variety of different physical applications like human-made, natural, or climatological conditions that dictate the type of structure to be used at a given crossing. This could be in the form of so this can be some of the basis for the choice which particular structure type will be used on a particular physical application, whether it is human-made, natural, or climatological conditions. So the first one is the length to be bridged from the start to the end of the structure. So that's one of the bases for us to decide what particular type of structure will be used on a particular location. Another reason or another basis is the depth of channel or ravine to be crossed. Another is the underpass clearance required, the type and volume of vehicular traffic, the extreme temperature conditions, the precipitation or snowfall, curvature of overpass alignment, aesthetics of the surrounding environment, and lastly, potential environmental impacts. So these factors that we have enumerated here can dictate which type of structure will be used at a given crossing. So since we are talking about now on the term structure types, there are actually several types of bridge structure that can be made depending on the location, depending on the location, or depending on the different factors that we have enumerated here. So the first type of structure, bridge structure that we will study is the slab-on girder. S- Slab-on girder looks something like this. So this is actually the most common type of bridge structure. That's why we will be more focusing on bridge structure of this type on our study of bridge engineering, the slab-on girder structure type. A bridge superstructure consisting of a concrete slab resting on a set of girders which are connected by diaphragms to form a frame. So that is a slab-on girder. There is a slab that is being supported by series of girders that will form a frame. The girder could be steel or precast pre-stressed concrete beams or of other suitable material. So these supporting diaphragms or primary members or girders can be made out of steel or precast pre-stressed concrete beams. Traffic passes over the top of the slab, which can be covered with a wearing surface, although sometimes the slab itself is made thicker to create an integrated wearing surface, like using a portion of the slab rather than a separate layer to resist the wear of traffic. So this slab that you are seeing here on a slab on girder type of bridge structure can be covered with a wearing surface. So there's an additional layer of surface that will be put on top of the deck, like bituminous material or asphalt. Although this wearing surface can be made uh, integrally with the superstructure itself, like the slab can be made thicker so that there will be no need to add additional layer of wearing surface. So the slab will just be made thicker so that there will be no need to put additional layer of wearing surface. So that's one type of bridge structure that is usually constructed. And actually this is again the most popular on this time in the modern highway bridge time. Slab on girder is the most popular type of bridge structure that we usually construct nowadays. That's why we will be more focusing on the design and or engineering of a slab on girder type of bridge structure. So there are actually many advantages of using slab on girder type of bridge structure. So one of these advantages is this. One of the advantage of using slab on girder type of bridge structure is because the design of slab on girder is very simple. Its design is simple. From an engineering perspective, slab on girder structures do not break much new ground theoretically, but the complexity they offer from a total project perspective presents a challenge for any designer. So that's one advantage of using slab on girder type of bridge structure. It's because its design is simple. You don't need additional knowledge for you to be able to design a slab on girder. You can use the knowledge that you have earned from the previous designs that we usually encounter in civil engineering, like design of reinforced concrete, design of pre-stressed concrete, or design of steel members. You don't need additional theoretical background just for you to be able to design slab on girder. And that fact is actually an advantage of using slab on girder type of bridge structure. It's because its design is simple. You don't need again to have additional theoretical background for you to be able to design it. So that's one advantage of slab on girder. Another advantage is the slab on girder bridge lends itself well to a uniform design that can be standardized easily. Standardization minimizes the need for creating a plethora of codes and specifications for designers to follow, especially when many owners of bridges rely on private consultants to assist in the design of new and rehabilitation of existing bridges. Uniformity also means that consistent and therefore economical methods can be employed in repairing deteriorated structures. Imagine if a highway network had hundreds of unique designs with customized components for each structure. So this is again another advantage of using slab on girder. It's because its design can be easily standardized, meaning we don't need to have uh, a new set of codes and specifications for the designers to follow. We can easily standardize the design of slab-on girder, we can easily make a uniform design out of the design of a slab-on girder that can be easily followed by designers. We don't need to have to 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 have new sets of codes and specifications to follow just for us to be able to design a slab-on girder type of bridge structure. So that's another advantage of using this type of bridge structure. Its design can be easily standardized, and due to that, we don't need to follow several series of new set of codes and specifications just for us to be able to design it. So that's another advantage of slab-on girder. Another advantage is that construction is relatively straightforward and makes use of readily available materials. Prefabricated primary members such as steel wide flange stringers or pre-stressed concrete beams allow for quick erection and a clean appearance, and at the same time provide for an economy of materials that is a benefit to the contractor as well as the owner. So this is again another advantage of using a slab-on girder type of bridge structure. It's simply because its construction is relatively straightforward. Its construction is somehow easy to be done. And in addition to that, the materials that are needed to construct it are usually readily available because there are prefabricated primary members such as steel wide flange stringers or pre-stressed concrete beams that can allow for quick erection of a slab on girder type of bridge structure. So that's another advantage of using slab-on girder type of bridge structure. It's because its construction is simply straightforward, and actually because of that, uh, since there is no special construction technique that is needed to construct a slab-on girder type of bridge structure, therefore the cost of constructing it can be minimized. And again, that is an advantage to the contractor as well as the owner, and as well as the availability of the materials that is needed. So you don't have to 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 fabricate specialized materials just for us to be able to construct a slab on girder. So that can save uh, money or cost to the contractor as well as the owner because of the readily available materials. So if there are advantages of using slab on girder type of bridge structure, there is also a disadvantage. So what is the disadvantage of using slab on girder type of bridge structure? The only advantage that we have here of using slab on girder structures uh, is it will be primarily used for short to medium span lengths up to 300 feet or 91 meters or for steel girders, and 160 feet or 49 meters for pre-stressed concrete girders. So that's the only advantage that we have here of using slab on girder. We can just use this type for short to medium span lengths. So for lengths of greater length, I mean for spans of greater lengths, we have to use other type of bridge structure because again the disadvantage of slab on girder type of bridge structure is that it is limited to short to medium span lengths. So another type of bridge structure that is usually used in construction is the one-way slab type of bridge structure. It looks something like this. For a very short span, like less than 30 feet or 9 meters, a one-way cast-in-place reinforced concrete slab supported on both ends by small abutments is an economical structure. So if the span that will be connected by a bridge is very short, like 30 feet or 9 meters, one-way slab type of bridge structure is an economical choice. So in a one-way slab type, we have a one-way slab here that is being supported by two abutments on each ends of the one-way slab. So when we say one-way slab, the slab just bends on one direction. That's why it's called one-way slab. The bending just occurs on one direction, which is this. For short to medium spans, like 30 to 120 feet or 9 to 36 meters, adjacent slab bridges, which are composed of precast prestressed concrete slabs, are the most common type of one-way slab bridges. So that is the most common type of one-way slab bridges that are usually used, which is the precast prestressed concrete slabs. The precast slabs may be of solid rectangular sections or box beams with longitudinal shear keys along their sides, so they will deflect together and share the live loads. So that is one-way slab type of bridge structure. It is composed of one-way slab supported by abutments on each end. So you usually use that for very short span of 30 feet or 9 meters. Another type of bridge structure is the steel and concrete box girder. So it looks something like this. It is just a box girder that can be made out of steel, or in this case, on this particular photo, it is made up of concrete. So that is usually used when bending and torsion are major concerns. So that box girder type of structure can offer an aesthetically pleasing, albeit expensive solution. Since these types of structures do not make use of standardized prefabricated components, their role is usually restricted to major highway bridges that can take advantage of their ability to meet relatively long span requirements. So we usually use box girder type of bridge structure for relatively long span uh, requirements. So you can see here that uh, although the only disadvantage of using box girder is it is expensive because there is no standardized way to prefabricate its components. Although, as you can see here on the photo, one of the advantages of using box girder, other than it is useful to for relatively long span, other than that advantage, uh, you can see here on the photo that uh, the space inside the box girder can also be used for additional traffic, although for light traffics only, like light vehicles or pedestrians. So the heavy traffic that will be accommodated by box girder can be put on top of the steel or concrete box girder itself, and then the clear space inside the box girder can also be utilized as additional pedestrian way or an additional road for light vehicles. So that can be another advantage of using steel or concrete box girder, other than its usefulness for relatively long span requirements. So another type of bridge structure that is constructed in a highway bridge site is what we call cable stayed. So cable stayed type of bridge structure looks something like this. Concrete or steel multiple cell box girders are commonly used for the superstructure of cable stayed type bridge structures. Although steel trusses and steel plate girders may also be used. Towers, also called pylons, are built with either solid or hollow concrete sections, depending on the tower size and the loads from cable stays. So the pylons or the towers are this part of the cable stayed structure type. So the pylons or the towers are the ones which support the superstructure or the deck itself. So as you can see here on the figure, the cables that supports or that support the deck or the superstructure are attached to the pylons or the towers. Superstructure may be designed to be supported at pylons with bearings, to be fixed at pylons, monolithic with pylons, or to be floating or no support at pylons. Low cost, ease of construction, and aesthetics are the major reasons why this type of structure is now a popular choice for medium and long span bridges. So one of the advantages of using cable stayed type of bridge structure uh, is it is good for serving long span bridges. So as you can see here on the figure, cable stayed type is used to support long span bridges. So again, as you can see on the figure, in a cable stayed type of bridge structure, the superstructure or the deck is being supported by cables that are attached to a tower or a pylon. So that is another type of bridge structure, cable stayed type. So another structure type or type of bridge structure that is usually constructed is what we call suspension type of bridge structure. So the most famous example of suspension bridge or suspension type of bridge structure is the Golden Gate Bridge that is that you're seeing here on the GIF or the figure. Trusses or steel box girders are typically used for suspension bridges. Vertical loads from deck are supported by hangers which are supported by main cables. Suspension bridges are very structurally efficient, thus they require less material than other types of bridges with similar span length. Because of their slenderness, detailed wind analysis is required to ensure stability. So in a suspension type of bridge structure, the superstructure or the deck is being supported by hangers. So these are the vertical cables that you are seeing here. So these hangers that you are seeing here are attached to a main cable, and then these main cables are attached to the main supporting towers. So suspension bridges are structurally efficient, meaning they require less material compared to the other type of bridges. Although suspension bridges are somehow slender, that's why they are critical with respect to wind or lateral loads. That's why whenever we design suspension bridges, we must ensure that detailed wind analysis is conducted so that we can assure that the suspension bridge will be stable. Because if we will not design the suspension bridge properly, uh, its fate will be maybe the same to the fate of Tacoma Bridge. So Tacoma Bridge is another famous suspension bridge that was built long ago before the construction of the Golden Gate Bridge. So you can search on the internet the words Tacoma Bridge, and you can see many articles and videos about it. So the Tacoma Bridge is another example of a suspension bridge, and if you can see on the internet, the Tacoma Bridge is a very flexible suspension bridge to the point that it it uh, it swings back and forth even though there is no major wind load that that is being experienced by the superstructure, or even though the traffic volume is just the or are just the users of the superstructure. You can see on videos that the flexibility of the Tacoma Bridge. So that flexibility actually became the reason of its sudden failure. So the Tacoma Bridge is actually one of the uh, most famous failures of bridge construction in the history. And although the failure that we had experienced on the Tacoma Bridge were not put into waste, because we have learned many things on the failures that our previous engineers experienced on the construction and the design of the Tacoma Bridge. Actually, our specifications, our codes that we use nowadays on modern highway bridges are actually built with the foundation on the failures that we learned from the design of the very flexible Tacoma Bridge, very slender Tacoma Bridge. So that slenderness, that flexibility became the cause of its very sudden failure. Another type of bridge structure is steel or concrete arch. So this is an example of steel arch. This is actually the Sydney Harbour Bridge that can be found in Australia. When the deck is suspended from the steel arch, the structure is called a through arch, just like what you are seeing here. This is actually an example of a through arch. So when the supporting arch is located above the deck, so it's called through arch. When the deck is supported on top of the arch, this is called a deck arch. So if you can see a bridge with an arch located below the deck, that is actually what we call the deck arch. The arch is located below the deck. An arch bridge generates large reaction forces at its end supports. The horizontal component of these reaction forces is resisted by either abutment foundations or, in the case of a tied arch, a tie between arch supports. The highest point on an arch is known as the crown. So this is the crown. The highest point in an arch. In a true arch, the vertical cables from which the deck is suspended are called hangers. So these are the hangers. These vertical cables that you are seeing here. In deck arches, the area between the bridge deck and the arch is known as the spandrel. So if you will look on this true arch, although this is not a deck arch but a true arch, but you can already see here the word spandrel. You can see here the area that is being described by the word spandrel. So the spandrel is actually the area between the arch and the deck. So this is the spandrel or a deck arch, although this is a true arch. Deck arch bridges with open areas between supporting columns are known as open spandrel arches, while those that are solid between the arch and deck are called filled spandrel arches. The spring line is the extension of the arch from the abutment or pier support. So in this figure, you can see here an extension of the arch. So this is the arch, and this is an extension of the arch. That is what we call the spring line. So that is extended through that is extended to the abutment, up to the abutment or pier. The surface that the arch is supported on is inclined at an angle. This surface is called the skew back. The lower surface of an arch is the soffit. So if this is the arch, the lower surface, which is this, is called the soffit. And the upper surface, which is this, is called the back. So those are just some of the major parts of an arch bridge. Arch bridge. So arch bridges are also useful for medium to long span bridges. So it can be made out of steel or concrete. The arch supports. The arch support can be made out of steel or concrete. So the last structure type or the last type of bridge structure that we will study is the truss type of bridge structure. So the truss members of a truss type of bridge structure are typically fracture critical members, meaning there is no redundancy in the load path. So should one member fail, the whole structure would collapse. The construction and maintenance costs of truss bridges are very high. Due to this, very few truss bridges have been built in the past 50 years. So truss bridges are actually useful to carry heavy loads, heavy traffic, such as the railways of trains, such as this railway that you are seeing here on the picture. Although the disadvantage of using a truss type of bridge structure is that its members are fracture critical. So when we say fracture critical, it just means that if one member fails, the whole structure might collapse. So for a truss bridge, for a truss type bridge, maintenance is very important so that to ensure that every member of the truss is in good condition. Because as I've said before, the members of a truss is fracture critical members. So meaning that just means that whenever or should I say if one member of the truss fails, the whole truss structure will collapse. So there must be a very delicate maintenance of every member of the truss just to ensure that the members are in good condition. So due to this critical maintenance, this results in a high maintenance cost. In addition to the high construction cost of truss bridges. So due to this high maintenance cost of these truss bridges, very few of this type have been built in the past 50 years. So we don't usually build truss bridges nowadays due to the high maintenance costs. Although there are still truss bridges, actually in the Philippines, we can still see some famous truss bridges like the Ayala Bridge. So if you had been on Manila, you are very familiar with the Ayala Bridge, which is composed of steel truss members. So those are the different some of the different types of bridge structure that we we can build on a particular highway bridge site depending on the condition of that particular site. So on the decision of what type to be used depends on the different factors that I have enumerated a while ago, as well as the actual site conditions. So again, among those different structure types that we have discussed, the slab on girder type is the most common nowadays. That's why in our subject, in our course, bridge engineering, we will be more focusing on studying slab on girder type of bridge structures. So there, we are now done in addressing our fifth and last goal for this discussion, which is for you to be able to define the different structure types used in bridge construction. So just to summarize what we have learned on this discussion, let me just uh, review or have a recap of what we have learned on this discussion. So on this discussion, we have learned that bridge engineering is an engineering discipline branching from civil engineering that involves the planning, design, construction, operation, maintenance, and rehabilitation of bridges to ensure safe and effective transportation of vehicles, people, and goods. So as I mentioned a while ago, uh, bridge engineering is different from bridge design. Bridge design is actually another subject, another course that you have to take after you have taken bridge engineering. Although again, in our school, in our curriculum, we have no bridge design. We have no separate bridge design course. So we will try to study everything about bridges in our course, Bridge Engineering. Although again, as I've mentioned, bridge engineering is actually a broader subject than bridge design, because actually bridge design is just a part of bridge engineering, as you have seen on our definition. Because bridge engineering encompasses everything about bridges: the planning, the design, the construction, the operation, the maintenance, and the rehabilitation. So we can clearly see that bridge engineering is a broader subject than bridge design. So in our subject, in our course, bridge engineering, we will not be focusing more on the design of bridges, but we will be discussing everything about bridges: the planning, design, construction, operation, maintenance, and rehabilitation. Another thing that we have learned on this discussion are the parts or the different parts of a bridge. So we have learned that there are actually general terms that we usually use to describe the different parts of a bridge, namely the superstructure. So the superstructure comprises all of the components of a bridge above the supports. And then another general term that we usually use to describe the different parts of a bridge is the word substructure. So substructure consists of all elements required to support the superstructure, or in other words, substructure are all of the elements that are below the superstructure, or vice versa. Superstructure are the elements that are being supported by the substructure. And then last general term that we usually use to describe some parts of a bridge, although these things are not actually part of the bridge, although they still play a vital role with respect to the functionality of the bridge. So we call those as appurtenances and site-related features. So appurtenance is any part of the bridge or bridge site that is not a major structural component yet serves some purpose in the overall functionality of the structure, like guardrail or the bridge barrier or the traffic barrier, etc., etc. So these appurtenances are still, we can still call them part of a bridge, although they do not play a vital role on the structural support of the whole bridge. But still, they play a vital role on the overall functionality of the structure, our bridge structure. So lastly, we have learned in this discussion the different structure types, which are slab on girder, one-way slab, steel and concrete box girder, cable stayed, suspension, steel and concrete arch, and truss. So we have learned that these different types of bridge structure, uh, actually has their own advantages and disadvantages over the other. So the choice of which structure type to be used depends on different factors that we have enumerated before on this discussion, as well as uh, on the actual site conditions. So those are the things that we have discussed and we have learned on this discussion. So that's all for this meeting. Thank you for listening. If you have any questions, clarifications, or any other concern, please do not hesitate to contact me via Canvas inbox. So if you will go on Canvas, you can see this small icon here on the left side of your screen, the inbox. So you can click that and message me if you have any concerns, clarifications, or any questions in general. Or you can message me on Messenger or Facebook. Just search my name, Adam Stress Nuevo Junicio. Or you can email me at arjunicio.c@tip.edu.ph. So that's all for this meeting. Thank you for listening and have a good day.